Hello, everyone, and welcome to Algebra 2, Section 4.8, Analyzing Graphs of Polynomial Functions. So I really like this section because I think it'll help you see how far you've come and how much you've learned. Just by looking at these functions, see if you can match them with their graphs. Of course, I will go through it with you, but look how much you know already. Hopefully you know that A and B are both parabolas. They're both upward parabolas because the leading coefficient is positive. And then on top of that, you know that this one has a y-intercept of 0, -4. And this one, also an upward parabola, has a y-intercept of 0, 2. So I looked down at my chart and I only see two parabolas, C and F. And this one has a y-intercept of 0, 2, and this one 0, -4. So right away, I know that this one is C and this one is F. For the next one, it's cubic. There's two cubic graphs. So I see a cubic graph here and a little bit hard to see there, but E is cubic. Ooh, D looks cubic. So I actually have three choices, even though I only have two that actually say cubic. So one of them must be the fifth power. So right away, let's skip to the fourth then. There's only one that could be the fourth and positive and has a y-intercept of 0, -1. So that is definitely going to be B. So sometimes a fifth power function can look cubic because it maybe doesn't have that last little bump. For whatever reason, it just doesn't have enough going on that it actually made another bump, so it looks cubic, or maybe it has just a slight bump that you don't see. But all odd powers start at the bottom and end at the top, unless the leading coefficient is negative, and then they start up and end down, which is going to be our next clue, in that this one is definitely going to end up and has a y-intercept of 0, 1, where these two are going to end down. So I look for my cubic that ends up, and I see that it's A, and it does cross at 0, 1. So hopefully you're seeing how much you've learned about the nature of a graph just by looking at its function. I can easily tell which one is the fifth. This one should be a little steeper because it has a 2 as the leading coefficient, but also it's going to cross at 3 versus this one's going to cross at -2. So here's my -2. So this is going to be D. It's going down, y-intercept of 0, -2. And then in addition to that, this last one is going to cross at 3. So there must be more going on to this. It's definitely steeper looking than, say, D. But I can't see any other bump. So 0, 3. This one's E. So now we've matched them all. And honestly, that was just review. That is not at all the point of today. Today, you're going to be learning about maximums and minimums. So it says next, the graph of every polynomial of degree n has at most n1 turning points. So what that means is this is a cubic function. So it's going to turn at most 2 times. So this is n. So n minus 1 is 2. And sure enough, it turns here. That's called a turning point. And then it turns here. Where this is an x squared function, so since n is 2, it's going to have at most n minus 1, which is 1 turning point. And that's where it turns. It goes down and it turns back up. On this next one, we decided that e was to the 5th power. And therefore, n is 5. It has at most 4 turning points. And of course, it doesn't. We only see 2. So remember, that's not always how many turning points it has, but the most number of turning points. And if a polynomial function has n distinct real zeros, then it actually should have n minus 1 turning points. So again, looking at E, we decided that E was x to the fifth, but we can only see 3 of the zeros. If we could see all 5 of the zeros, if there were 5 real zeros, then it would have 4 turning points. 1, 2, 3, 4. So honestly, I think that this little section here is summing up that's something that's kind of intuitive, but there it is written out for you. So we don't actually call these turning points. We call them maximums and minimums. So on your graph, any point that is higher than all the nearby points is called a maximum. So it's not the maximum of the whole graph. This graph continues to go up, and this graph continues to go down. So this isn't the overall minimum, and that's why they gave it the name local max and local min. They're just higher than everything around them. So let's say you're the best soccer player on your team. Then locally, you might be the best. You might be at the top of your game. But if you suddenly went into a competition with other schools or other counties or even other states, then you might not be the maximum. That's how I kind of think of it with a graph. So compared to everyone else around you, you might be at the top, but on the overall graph, there might be someone or something higher. So we cannot find those points, these minimums and maximums, by hand until you get to calculus. Not even pre-calculus will allow you to do it. So right now, we're going to have to do it on our calculator. The only ones that you are capable of doing by hand are parabolas. So C and F you could do by using negative b over 2a. That does give you the x-coordinate of the vertex, which is either the max or the min. So if you have a parabola, then you can do it. But on these cubic functions or functions to the fifth power, you're going to have to use your calculator for a couple more years until we get to calculus and I teach you how to do that. So let's go ahead and do that on our calculator. So I went ahead and typed in equation C, x cubed minus 2x squared minus x plus 1. So remember that if you're not sure where you left off with what kind of strange word problem, you can always hit zoom 6 and that'll put it someplace more normal. And if you see that you're just looking at a smaller portion of the graph, an even better favorite is zoom 4. So I can see that the maximum is somewhere between -1 and 0, but I don't know exactly what it is. So I'm going to use second trace, which is I really want second calc. And then I go down and I actually say I want the maximum. So I go to number 4, or you can scroll down. Either way, it's going to ask you for the left bound. There's 2 ways to get it. It's pretty much saying between what 2 numbers. You can either scroll over until you're clearly to the left. So I'm going to hit enter. Or you can just hit a number. So for right bound, I might say, well, I think it's between -1 and 0, but it's definitely between -1 and 1. So I could just type in a 1, hit enter. And what you've done is you've given it 2 numbers to look between. So you're saying, I think it's between -1 and 1. It does ask you to make a guess, but the guess isn't really important. So you can just hit enter. When you get to calculus, I'll explain why they make you make a guess. The algorithm that's in the calculator doing the work needs a guess to start. And there you go. The maximum is -0.215. Please remember to use 3 decimal places. Comma, it's an ordered pair, 1.11. And for correct rounding, it would be 3, 1.113. So I will do one more of those. This time I'll do the minimum. But I don't usually do this, but this is really just an exercise in making sure you get this. And if we were in class, I would probably give you a certain number of minutes while I walked around and make sure everybody had it, but I wouldn't actually make you do all 6. So you may pick any 3 on the worksheet and I will be looking for them when I check your notes. But I will do one more. I'm going to do the minimum. So second, calculate. This time I'm going to select number 3, which is the minimum. So my minimum is definitely on the other side of this left bound, so I could actually just hit enter right now. But for my right bound, I'm going to have to pick something beyond what I think is the minimum, which is maybe 1.5. So I could say 2. So I'm going to hit 2. And it gives you these great lines. It's saying, do you think the minimum is between here and here? And I do. I think it's right there. I don't worry about the guess. I just hit enter. And there you go. 1.54, make sure you round correctly, 9, comma, negative 1.631. And that's how you find the minimum and the maximum. So you need a total of 3. I've done one of them for you. You can pick any 2 others. I shouldn't say any 2, not the parabolas, which you can do by hand. So pick one of the cubic, quartic, or the function to the 5th power, and find maxes and mins. So these next 3 problems, you're welcome to do on your own, but if you want to watch the first one, just to kind of make sure you understand and remember all that you were supposed to learn this chapter, these are just kind of putting it all together. So the first thing that we learned was just the general shape of graphs. So I hope that you can see that this is actually an x cube graph without multiplying it out. But if you were to multiply it out, it'd be x times x, and then this one's squared, so there's one more x. So I look at this and I know that it's a cubic graph. The leading coefficient is positive, so I know it's going to end up. I can find the x-intercepts by letting y be equal to 0. And if this is 0, then x would be negative 3, or x could be 2, and that would also make my equation equal to 0. And then we also learned that if a 0 is repeated an even number of times, it's going to create a bounce. So I'm going to bounce at 2, 0. So I'm going to go ahead and plot this. And then I'm going to get my y-intercept. Remember that a y-intercept is the opposite. Instead of y being 0, the x is 0. So y is equal to 1/6 times 0 plus 3 times 0 minus 2 squared. I'm just going to tell you right now, a lot of kids multiply this all the way out just so they can find the y-intercept. Don't do that. It's a complete waste of your time. And you know how long my tests are. You definitely do not want to waste a minute. So instead, you can just multiply this out. This is 12. Remember, when you have a whole number times a fraction, you can make them all into fractions if you want to, so that you can do numerators times numerators and denominators times denominators. Making a whole number into a fraction is usually people's most successful way of multiplying whole numbers times fractions. And I get 2. So the y-intercept, when x is 0, y is 2. And now I have enough information to make a graph. I'm going to start down. I'm going to go up. I'm going to make sure that I bounce right there. And then I'm going to keep going up. Do I know how high I should have gone? I definitely do not. If you were really trying to make a more accurate graph, then you could plot one more point. So a nice easy point to do might be -2, just to see how high that goes. So 1/6, -2 plus 3, -2 minus 2 squared. So that's 1/6 times 1. -4 when it's squared is 16. And again, when you're trying to multiply whole numbers by fractions, sometimes it's easier to do fractions times fractions. And that reduces to 8/3, which is 2 2/3. So did I go too high? I went way too high. At -2, it only would have been 2 2/3. It only would have gone that high. So if you want to get one more point, you could do that on a test or a quiz to kind of make sure that you were doing things more accurately. But on your homework, what we did the first time around is plenty, okay? So just to redraw this with our new point, you could do something like that. I know I kind of missed it there, didn't I? All right, here's my one warning. If you choose to make another point, I cannot tell you how many kids then make that the max or the min, and it's not. So just because you plotted it doesn't mean, so look how I tried to stretch to make that work. It's not natural. You definitely want to keep the flow of the graph. I want to get to that, but I want to come back down to that. Okay, so the red one would have been a nice graph, but if you choose to plot an extra point, please do not assume that it's the maximum or a minimum somewhere. All right, I highly recommend that you try these next two on your own and then just skip ahead in the video and see if you got them right. But we are going to do them out. Again, this is cubic. I see an x and then two more x's. It's going to end up because the leading coefficient is positive. My x-intercepts are going to be -1 will make a 0, and 4 will make a 0. And 4 is a bounce. My y-intercepts are when y is equal to 0. Sorry, when x is equal to 0. So I'm going to go ahead and plug that in. Y is equal to 1/2 times 0 plus 1, 0 minus 4 squared. Y is equal to 1/2 times 1 times 16, which is 8. So when x is 0, y is 8. 2, 4, 6, 8. I know I need to bounce at 4. 1, 2, 3, 4, and -1. This is not the maximum. I mean, it could be, but the chances are really slim, especially looking at how the graph goes. So it's important to me that when you graph this, you go through and then you go like that. Okay. This is not one where I felt like I needed an extra point. I can tell I'm not going to go that much higher in order to come down for a nice graph. This line, this point right here, gave me a really good sense of it. Where in the last one, I feel like the blue graph might have been it. It might have been really steep and then come back. But the red one does look a little bit more natural. So on this one, I don't think I would get an extra point. I think I like it just the way it is. Last one. So again, it's cubic, x times x times x. And it's going to end up, so I know its general shape. I know that the x-intercepts are -2 will make a 0, 1 will make a 0, and 3 will make a 0. And then for the y-intercept, 0 is equal to, so if you were to multiply this out, the y-intercept would be really easy to find because plugging in 0 to an equation that looks like this, x cubed minus 3x squared plus 2x plus 1 is great. If x is 0, the answer is just 1. But I wouldn't go through the trouble of multiplying this all out just so you could plug in 0. It's so easy to plug in 0 at this stage. So 1/4 times 2 times -1 times -3. If you multiply those three together, you can think of them as one fraction. You get +6. And like I said, if it helps you to make it over 1, you can do that, which would be 6/4, which is 3/2, which is the same as 1.5. So when x is 0, y is 3/2. So when x is 0, y is 3/2. I also have my -2, my 1, and my 3. So again, not the maximum. Could be, but extremely unlikely. So to get a good shape, I would go above it, but then I would come back down. Is that the perfect shape? That's okay. I don't really need the perfect shape. I'm trying to show you that you can get a pretty good idea of what this graph looks like with all that you've learned this chapter. So mathematicians have decided to categorize even and odd functions. An even function is when f of -x is equal to f of x for all the x in its domain. In short, it's symmetric around the y-axis. So you can see that if you have the point 2, 3, then you must also have the point negative 2, 3. That's an easier way to think of that. Negative 2 is going to produce the exact same answer as 2 is. For an odd function, if you have a point like 2, 3, then you would also have the point negative 2, negative 3. It's symmetric around the origin. So it's kind of like having one of those little spinner toys where it, like you blow on it and then this thing spins around. And unless it's different colors, if you had this side being red and this side being blue, then you would be able to tell when you spun it around whether or not it was back to its original position. But if both of them were red and you gave it a little spin, you might not be able to tell if the bottom was still on the bottom and the top was on the top. That's how I think of an odd function. It could kind of spin and end up in the same location. So even function, you can fold like a book, right? And the things on either side would line up. And for an odd function, it's kind of like a spinner. Odd functions will always include the origin, 0, 0 on every odd function. And that'll help you decide right away. That's an easy way to tell if it could be odd. Not every function that goes through 0, 0 is odd. There's one that goes through 0, 0. It's not odd or even. Okay. Determine whether each function is even, odd, or neither. So first of all, let's just run through all their shapes. This one is cubic, ending up. This one is quartic, also ending up. Cubic ending up. A parabola going down. Quartic going up. N to the 5th power. 1, 2, 3, 4, 5. Ending up. So right away, your only shot at odd functions are going to be ones that have this down to up. They have that diagonal concept. So this could be odd. Could be odd. Where these could be even. But of course, it's not quite as simple as that because you have to add the axes in there. If it's not actually symmetric around the axis, if it goes like this, then it's no longer even. So I want you to get the concept that it's just not this easy. You can't sit there and say that just because it's got that general shape, it has to actually fit around the axis. So it would have to be like that. If it's off center at all, then it's no longer even. Even, not even. So it's not just symmetry within itself. All parabolas are symmetric within themselves. It has to be symmetric specifically around the axis. So while we're on it, let's do our even functions. So what does this function do? It's negative x squared, but it's been moved up 5. They didn't move it left or right. This one isn't negative x, say, plus something, and then up 5. It's just been moved up 5. So this one is an even function. And that's what you're looking for. You're looking for something that's only been moved up or down for a parabola to make it stay even. So how do we know for, say, number 5? How do we know whether or not that's centered on the x-axis? Well, or on the y-axis rather. It's really easy to tell. I just plot 2 points. So if x is 1, then I get 1 minus 5, which is negative 4. So at 1, it's at negative 4. So if I see that at negative 1, it's also at negative 4. I may not know what the rest of the graph looks like, but at least I know that it's even. It's on the same on both sides. So I'm going to do negative 1. Negative 1 to the 4th is still positive 1. But negative 1 to the 3rd is negative 1 times negative 5 is positive 5, so I get 6. So I don't have to consider odd for this one. It's quartic. It's never going to be odd. But now I know it's also not even. So it's neither. All right. I don't know why I started at the bottom. Let's go back up to the top. So same thing. On this one, it's not enough for it to just have that general shape. It needs to be the same on both sides. So you can real quick check a point. So when x is 1, I get -6. So 1, -6. If this is truly odd, then -1 will put me up there. See, diagonal? -1 will put me up there at +6. And -1 indeed, -1 minus 7 times -1 does put me at +6. So this one is odd. So you might want to try the other ones on your own. But if not, of course, I am going to do them for you. So on this one, I know it could be even. It's definitely not odd. But I'm going to just check 2 points real quick. When I'm at 1, 1 plus 1 minus 1 is 1. If I'm at -1 and I also get 1, then I'm going to feel like it's even, or even around, it's symmetric around the y-axis. So I try -1. And -1 to the 4th is 1. -1 squared is 1. -1, it does give me 1. So this one is even. X cubed plus 2. So if I think about it, just graphically, it's an x cubed graph that's been moved up 2. Is there any chance that that's odd? Because you know it's not even based on the graph, but could it be odd? And the answer right away, without even my doing this little table thing, is no, because it doesn't go through the origin. And I can just see that this point doesn't translate to that point down there. So there's 2 ways to know that. So this one is neither. And last one, 2x to the 5th. So this one actually doesn't look like this. All these bumps are caused by all the other pieces that go with something. So when you start adding x to the 4ths and x to the 3rds and x squareds and x's and numbers, that's what creates all those bumps. If you just have 2x to the 5th, it just starts down and ends up. It doesn't get to have all the little bumpy pieces. That's why x to the 5th can look like x cubes. So it's missing all of those extra pieces. It does go through the origin. And if you want to just double check, then when x is 1, you get 2. So 1, 2 is up there. So -1 should make -2. And -1 does make -2. So this is definitely odd. So let's do some word problem applications. Number 1. During a recent period of time, the number S in thousands of students enrolled in public schools in a certain country can be modeled by the following equation. X is going to be in time, which is in years. Use a graphing calculator to graph the function for the interval 0 is less than or equal to x is less than or equal to 41, so a 41-year time span, and then describe how the public school enrollment changes over this period of time. So if you weren't doing this on your calculator, I think it'll be easier to visualize it by hand first. You're looking over a 41-year period in years, and you're going to be looking at this number of students, but in thousands. So sometimes they do that because they don't want to have to write too big a number here. But interestingly, the y-intercept of this is 36,000. So we know that this graph, which is cubic, is going to reach 36,300. But in thousands, that actually means 36 million. So this is a very challenging problem because it says students in thousands, and then you see thousands. But remember, it's the number of students enrolled in a public school in a certain country. So it makes sense that there are millions of students. And just to show you how easy a mistake this is to make, the answer in the back of the book missed the thousands. So they gave the final answer in thousands instead of, it turns out that it ends up being over 1 million. So we're going to have some kind of graph. It's cubic. So maybe from that y-intercept it goes up and then it goes down. Maybe that's what our cubic graph looks like. And they want us to describe this. So maybe the enrollment went up and then the enrollment went down and then it went up again. Or maybe the first thing that happened was it went down and then up. That would also be cube. Oh, can it be that though? It's positive, so can it end down? No, it can't. But we're going to do it on our graphing calculator. But I wanted you to have a concept of what our window is going to need to be. Our x's are going to need to go from at least 1 to 41, or 0 to 41. And our y, we don't need negative students, is going to go up to 36,300 or higher. Because if it goes higher and we're trying to figure out what the maximum population was, we'll need to go even higher than that. But it's good to think about it before you put it onto your calculator. So I've put our equation into the graphing calculator, but that wasn't the hard part. The hard part is going to be our window. Now remember, we already figured out that the max is going to go from 0 to 41 technically, but let's just go to 50 so we can see the entire thing. And that represents the time in years that we're going to see it. Now we need the y-axis. Now this represents students, so it's not going to be negative students. And because the y-intercept is 36,000, that gives me some idea of where I need to be, but the graph could go higher. So just to be safe, let's say 50,000. And now let's hit graph. And we can see it, which is excellent. Not all the way, maybe to pretty close to 41, but it just starts to go up after that. So remember that this is the population of students. The population is rising until a certain year and a certain number, and then the population of students declines, but then it starts to rise again. Let's find those 2 points. So second, calculate maximum. I'm definitely not to the left of my maximum, so I'm going to go all the way over to 2. And then if this was 50, 25 should do it. And do I want to find the maximum between there and there? I do. I don't really need to make a guess as long as there's only one possible answer. So the first answer is that around, there's not really an answer, they just asked you to describe it. But I would say that the population was increasing for the first about 12 years. And then around the 12th year, they reached a population, now be careful, not of 44,970, but this is in thousands. So it's 44970,000, which actually makes this 44,970,927. And then all the way until, let's do our minimum, number 3. So we can start at, say, I don't know, maybe 20. And I would just go all the way over to 45. Well, you don't really need to go past 41. And the minimum, I don't ever make a guess. So close to year 30, they hit their low of 40078,000. So 40,078,211. And that's how you could describe this graph. Quonset huts are temporary all-purpose structures shaped like half cylinders. So there's a picture of it down there. The surface area, S, of a Quonset hut is given by this equation. Given that you have 1,100 square feet of material to build a Quonset hut, write an expression for L in terms of R. That means that your expression should be L is equal to an expression with the variable R. So let's go ahead and write down what they gave us, which is S, surface area, is pi r squared plus pi r L. But then they told us that we've been given 1,100 square feet of material to build it. So building material is used and correlates to surface area. So I can write 1,100 right here. If that's the surface area, then that's how much material I need. Pi r squared plus pi r L. So when they say write an expression for L, I need it to say L is equal to. So think about it this way. if you had something simple like 5 plus 2L, you wouldn't hesitate. You would subtract 5 from both sides and then divide by 2. You know order of operations, what comes first in solving. We need to do the exact same thing here. We need to subtract first and then divide. So I have 1100 minus pi r squared is equal to pi rl. And now we can divide both sides by pi r. Now be careful. You don't want to cancel these pi's or these r's. You can't undo subtraction by division. So you're stuck at this point. So your final answer is L is equal to 1100 minus pi r squared over pi r. And again, if you need another example of that, if you had 12 minus 5 over 5, that would be 7 over 5. It certainly wouldn't be 12, right? So when people see it with numbers, they don't tend to make that mistake, but when they see it in algebra, sometimes they do. So be careful. Now it says that the volume of a Quonset hut is given by this equation. Write an equation that gives the volume as a function in terms of R only. So right now, volume is a function of R and L. We want it to be R only by substituting in what we just got. So volume is equal to 1/2 pi r squared, and in place of L, I can now write 1100 minus pi r squared over pi r. Okay, so now follow this. Now I can cancel because this is being multiplied. That's what the parentheses mean, multiplied by this, which means multiplication and division do cancel each other out. If you multiply x by 3, but then divide by 3, you can cancel that out because they're inverse operations. So I'm going to cancel the pi, and I'm going to cancel one of the r's. So this represents 2. There's 1. And now I have 1/2 r, 1100 minus pi r squared. And of course, you can simplify that to 550 r minus 1/2. I'm not sure that that's simpler, but pi r cubed. Okay. So now I'm going to use my calculator to find the value of r that maximizes the volume of the hut. So in other words, this is a cubic equation of some kind. I didn't actually draw the whole graph. We know in general that cubic graphs go like this. I don't need to see the entire thing because I want the volume over positive values of r. When r is negative or when the volume is negative, that doesn't matter to me. So you don't have to do this step, but just to show you that it is going to cross 0, I do know one of the zeros. So 550 minus 1/2 pi r squared. So I do know that the graph, whatever it does look like, is going to cross 0. So maybe it comes down and it goes like that. I'm not really sure. But the bottom line is I definitely want to look at all the different r's. At some r, it's going to have a good volume. But at some r, it's going to have the best volume. This is the volume for different values of r. So let's go ahead and do that on our graphing calculator. So I typed my equation in already. You'll notice I didn't bother to use r. You can use r if you want to by doing alpha and then the times button, but that's a little bit of a pain. I would just switch it to x. I did use my fraction key in order to make a nice fraction there, and the pi button, which is above the caret. Now, the tricky part about this problem is that you have no sense of how big it's going to be. But we're talking about r being the radius of this Quonset hut. So how big could it be? Well, it's definitely not going to be a negative radius. And the radius could possibly go up to, I don't know, 10, 20, 50 feet wide. 50 feet wide would be pretty big. Let's try 30 feet wide. Remember, it's just a radius. So that actually would be 60. But let's just say that it was that big. But how big could the volume be? again, I don't need to see the negative volume, but if the area is about 1,000, the volume is going to be much bigger than that. So let's start with 10,000, but I definitely might need to go higher. We'll know in a minute just by hitting graph and, oh, that was enough. In fact, 10,000 was definitely more than I needed. So this entire cubic equation, we can't see the whole thing, but we can definitely see enough to say a radius of 2 is going to give me this volume, a radius of, 8 is going to give me this volume. I want to know what radius gives me the best volume. So that's the max. So I do second calc. I want number 4, which is the maximum. That is definitely not on the left side of my maximum. You can either move it over or you can just say 1. You know it's going to be bigger than x is 1. And for the right bound, if you're not sure where that is, then you can scroll until you get beyond it. Or you can just take a guess. I don't know, 15 maybe? Yeah, that definitely ended up on the other side. So I definitely know that that max is between 1 and 15. I don't need to guess since there's only one possibility. And there you go. 10.803 will give you a volume of almost 4,000 cubic feet. Although the answer to part C just asked for the value of R. So your answer would be 10.803. Make sure you label it with feet. Number 3 says, a cylinder is inscribed in a sphere of radius 8 inches. Write an equation for the volume of the cylinder as a function of h. So you may remember that the volume of a cylinder is pi r squared h. We get that because pi r squared is the area of a circle, but then if you multiply it by h, you're actually going to end up with a whole cylinder. Think of it as a single disk, pi r squared, but then stacked up, one on top of another. That's how you get the h. So right now it has an r squared and an h in it. If they want v of h, that means I have to get rid of my r squared. So I need to figure out what r squared is equal to. So if you look at this little triangle right here, that 8 looks like it's on the bottom. It's a little deceiving. It actually is this hypotenuse right here. Now that I've drawn the whole triangle and it looks funny. And then the key geometry fact that you need to know here is that if the entire height of the cylinder is h, but you've inscribed the cylinder inside the sphere, then this one section will be half of h, or h divided by 2. So my r and my h over 2 is related by the Pythagorean theorem. R squared plus h over 2 squared is equal to 8 squared. R squared is equal to 64 minus h squared over 4. So I can put that right. Normally I would solve for r, but in this case I actually want r squared, so I can put it right there. And now my new equation with only h's in it is pi times 64 minus h squared over 4 times h. Now if you're going to do this on your calculator anyway, then there's really no need to multiply it out at all. You could just type it into your calculator just like that. So when you do that, we've talked about this several times now, this is going to be some kind of a cubic function. 64h minus h cubed. So I'm just going to multiply that just a little bit so you can really see that h cubed there. So, but because of this format, I can see that one of the zeros is 0. So let's say my volume equation looks something like this. So what this is going to tell me is at any h, I can tell you what its volume is going to be. Volume is the y value, and the height is the x value. So maybe at h is 1, I get this volume. At h is 2, I get this volume. And I keep getting a better and better volume. But eventually, I get a worse volume. How could that happen? Well, if you took this same exact sphere and you made H really small, you could do that. You could put this really short cylinder in there and your volume wouldn't be really great. Or you could put something like what they did. Or you could put something really tall. You could keep making H bigger and bigger and bigger. But if you make H too big, again, you're not actually going to maximize your volume. So all these different heights do have different volumes, and this cubic function tells you what that is. But which one are we trying to find? We're trying to find this maximum height, or the maximum volume. Maximum volume, and what height does that happen at? So I do want you to finally try one on your own. I don't want to just give you the answer, but I also want you to be able to check it. So my thought is, the question is, find the H that maximizes the volume. I'm not going to tell you that, but I will tell you the maximum volume. That way you can check your work. So the maximum volume should come out to be 1,238.22 cubic inches. So if you get that as your Y value for your max, then you know you've done it right. But go ahead and fill in that H, and that way when I check your notes, I can make sure that you're not just watching me, but actually typing these in on your calculator on your own and able to find that. Last one. You are making a rectangular box out of a 16 by 20-inch piece of cardboard. So let's say this is your piece of cardboard. What you're going to do is you're going to cut out identical size X's from every single corner. X, X. And then you're going to fold them up. So once that's gone, let's actually erase it. Once you do that, then you're going to fold up those corners along these dotted lines here, and it's going to make a really shallow box, like you would use for a tray or a, let's do something important, like a box of chocolates, okay? And its height is going to be X. This side, the distance of this side, if it was the entire thing, would have been 20. But since I've cut a little X out of both corners, this side is 20 minus 2X. And in my original, before I cut the X out, this side was 16. But once I cut that little corner out, that side, which I'm folding up along the dashed line, is 16 minus 2X. Now, I could have taken the same box and done it very differently. I could cut out a really enormous X out of all four corners. What would that look like when you folded it up? And if you were in class, of course, I'd be getting out my scissors and my paper and I would be showing you so that you could really see it. But hopefully you can see it anyway. Can you see what would happen if you folded this up? This side would be like the front, and it would just be really narrow, like a cereal box. Okay, but if this was originally 20, and I've cut out these two X's, this side is still 20 minus 2X. It just depends on what X is. And then this side is also used to be 16, but after you cut these two X's out, it's 16 minus 2X. So this side is 16 minus 2X. And how tall is the box? Now think about it. If you cut out an X-shaped box, when you fold this flap up into the sky, it's going to be X tall. So the volume, no matter which way I do it, the volume of the box is length times width times height, which is 20 minus 2X, 16 minus 2X, and X. So this is, if you multiplied it out, going to give you a cubic equation it's going to have a 2x and a 2x and a 2x. So it's going to have a 4x cubed as its leading coefficient. It's going to have a lot of other stuff too, but if you're going to do this on your calculator, you actually don't need to multiply it out. Your calculator is perfectly happy to let you type it in just like that. So on the outside chance you weren't able to get this number, I'm going to do it one last time. I'm going to show you how to find the x that makes that work. So I go to my y is equal to, and you can just hit clear for whatever's there. And then you can type this in just like you saw it, 20, if I can do it right, 20 minus 2x times 16 minus 2x times x. You don't need parentheses around the x. Juxtaposition, also, which is side by side, also means multiplication. But remember, if you hit graph, you're okay. We saw a little something, but that graph might be confusing. Always start with zoom 6, and then I can see that the part of the graph I probably want to see goes out to at least 10. So maybe make your window, you don't care about the negative volume, but we'll leave it there just so you can see the whole thing. I'm going to go to 15, but for my y min and my y max, I really need to get up there. I can see that it was going really high. So let's just say 100. That's probably too high, but we'll look at it. No, it wasn't too high. Look at that. It really went high up there. So can you see the cubic shape of it? It went up and then down and then up again. So we're going to want that number in between here and here. So let's look for that. Let's go to, quit, window. And how high do you think you need to go? Sometimes I just go for it and I do 1,000, which is really probably too high. But if it is, it'll just be a small graph and that's okay with me. And it was too high, but at least I can see the whole thing now. And I can find that max. So I do second, calculate, maximum. I'm already pretty close to it, so I'm just going to scroll over a little bit. And then I'm going to scroll to the right. You have to get your right bound next. So as long as I get to the right of it, I can hit enter. And then I don't usually make a guess. And there it is. You need to cut out 2.945 times, just not times anything, 2.945, and it'll give you, we'll do the dimensions in a minute, and it'll give you a volume of 420. You are not going to beat that volume. So from my calculator, how big should I make the cuts to have the greatest volume? I should make the cuts 2.945 inches. And what is that maximum volume? That maximum volume will be 420.110 cubic inches. You don't really need the 0, but just to show you that I did go 3 places out. But the last question is, what are the dimensions of the finished box? So remember, these were the dimensions. After you cut that 2x out, 20 minus 2x is this side. So what you can do is you can store 2.945, store that as x on your calculator, and then just type in 20 minus 2x. Much easier for getting the answer, which is going to be 14.11 inches. And then 16 minus 2x is going to be 10.11 inches. So the final dimensions of the box are 14.11 by 10.11 by 2.945 inches. Lot to learn in this section. You guys did a great job. Have a good day.